살림 시디키고요. 그다음에 ThoughtWorks의 그 애자일 코치시고, 애자일 개발자시고, 리드 개발자시고, 개발자시기도 그리고 자기는 나이스 펄슨이래요. 박수 한번.
I don't.
저기, could you stand up, please? This is Matt Phillips from ThoughtWorks. He's a QA and lead QA. What's the best way to introduce you?
That's great.
Okay.
QA is fine.
네, 큰 박수 주세요. 살림이 지금 요 Essential Incidental Complexity of Software라는 제목으로 한 45분가량 세션을 가질 거고 그 뒤에 이제 질의응답을 할 거고요. Very much and please give him a big hand.
First of all, thank you all of you for showing up to this evening. I know some of you have had long working days. Some of you I personally know have had long working days. I want to thank all of you for coming up, especially people who finished their tasks early and came here. And I really want to appreciate and recognize Hubert for organizing this on very short notice. I asked him, I think Thursday or Friday, and he just said, Monday, can you talk? So I was like, okay. Hopefully I can be ready by Monday. So thank you, Hubert. So the topic of my talk is essential and incidental complexity of software. And I know you folks had received the PowerPoint slides. If some terms, there will be a lot of terms I will be talking about during this talk. If some of them don't make sense, you don't understand, please just stop me right there. This is a small enough group. We'll try to keep some time at the end for questions and answers, but feel free to just raise your hand. Or even if I'm talking fast, and you folks can inform them that we do this in the training, just stop me right there. It's perfectly fine, because I want to make sure with an audience this small, with a group this small, I want to make sure everybody understands what we're doing. Okay, so when I started to think about software in my early days, there were certain things that just seemed to defy common sense. It didn't make sense to me from other things that I knew from life or from growing up. And then I was drawn to other comparisons with projects and even technologies that didn't have any relevance to software. So here's a couple of old people. They're long gone. They're all gone and they've left this earth. Here's Charles Meggs. And this is Oliver Wendell Holmes. Why are they significant? They were both surgeons in the 19th century, so more than 100 years ago. And in the early 19th century, in the medical community, people did not know of the existence of germs, bacteria and viruses. We did not know that because they weren't powerful enough microscopes, or we did not have a way to examine the human body. So the germ theory about how diseases spread from person to person was just not known. So people had all of these ideas about disease is caused by talking to somebody or being close to somebody, but they didn't quite understand. So Oliver Wendell Holmes had this crazy idea that maybe germs came, there was something on our bodies, on our skin, that when we touch each other, we transfer and we make each other sick. And he was a surgeon, and he said there are a lot of pregnant women who die while giving birth. And he said, he thought, maybe something is in the surgeon's hands when we are touching a person, especially giving an operation or giving birth. We are transferring something bad. He didn't know germs, but he said something is going on, so we should clean our hands. He asked surgeons, we should clean our hands when we go for an operation. This gentleman, he was also a good surgeon, but he was totally appalled at that idea. And he came at it from what we call an aristocratic perspective. He reasoned surgeons are gentlemen, as in they are in the upper strata of society, and gentlemen's hands are always clean. Because we don't work like laborers, we don't dig dirt, we don't clean. So why are you asking me to wash my hands? You are defying common sense. So he opposed the idea of cleaning hands when surgeons, which are one of the, at least in England and in the Western civilization, were some of the upper strata people. He said to Oliver Wendell Holmes, your idea does not make any common sense. I can't understand it. Why are you asking me to clean my hands? My hands are clean. They're not dirty. They don't have ink on them. They don't have dirt on them. Why should I wash them? That was common sense. Turns out, Oliver Wendell Holmes was right. And Charles Meigs, for all his knowledge, was wrong on that. We'll come back to Oliver Wendell Holmes at the end of the talk. So this idea about some things that defy common sense led me back to how it applies to software. So here is a very long statement that I'll try to explain in its entirety over the next 30 minutes. A fluid, highly empowered team of skilled people is our best current offense against software complexity. I know it's a long statement with a lot of words and it's a mouthful, but I'll try to explain each of these terms: fluid, skilled, and software complexity specifically, and also the concept of teams. So let's start with the word essential. What is essential? Does then somebody want to take a guess?
It's basic.
Basic, yeah. Something that is very inherent or very related to the concept we're talking about. So when we break something down to its essence, where the word comes from, take away all of the complexity, take away all of the detail, what is left is the essence. So essential is something that is inherent to the problem domain or to the concept we're talking about. We cannot remove that. We cannot abstract it away. We can take other things away. So if you think about the concept of a car, at some level being able to move, if it's a car, is essential. It wouldn't be much of a car if it couldn't move. It may or may not have a roof. It may be a convertible. It may or may not even have wheels. In snow, cars have skids. But if it's a car, the ability to move is essential. Contrast that with the word incidental. Incidental is something that is not germane, that is not related to the concept we're talking about. It is something that can be removed. It may be the case that we see it as part of the picture, but it is not an essential part of the picture. It can be removed. It can be eliminated. So I'll talk about these two words in the context of software complexity. Now, here's an example. Here's a person tying shoelaces. Very simple task. Most of you who are wearing shoes with shoelaces did that. Showing this in 2 dimensions does not do it justice. A knot, a shoe knot, exists in 3 dimensions. So even in this picture, it's a 2-dimensional picture. I know it's a little hard to see with the lights. But in your mind, you're visualizing at this moment a 3D image. You're visualizing this hand, the right hand is behind the left hand. That's how you're visualizing. If you look at it and forget it, well, this is on a flat screen. There is no 3rd dimension. But you know that tying a shoelace is a 3-dimensional activity. It is, when I show it in a 2-dimensional picture, you supply the essential 3rd dimension in your mind. If I asked you to not think about this hand as behind, you won't be able to think that way. It is not possible to think about a shoe knot in 2 dimensions. It's a 3-dimensional problem, essentially 3-dimensional. So that's the essential part of tying a shoe knot. Now, here's a woman who is tying her shoelaces using only one hand. This is a very brave person. Her name is Jennifer Stimac. She was born with a congenital condition, a condition at birth, that she only had her left arm. She didn't have a right arm. It's a congenital condition based on genetic mutations that she didn't lose it in an accident. She was just born with one arm. So for her, and she's a very famous athlete now. She, despite her disability, she is now a motivational speaker and is a reasonably famous person in the U.S. For her, tying a shoelace with one hand is an essential part of the problem. When she solves this problem and she ties her shoelaces, she can only use one hand. So in her context, tying a shoelace with one hand is an essential part of the problem. For most of us who are blessed with two hands, this is not a problem we have to solve. We can and we do use both hands to tie our shoelaces. So one thing I wanted to get out is essential and incidental depends on context. For her, using one hand is essentially a part of tying a shoelace. She only has one hand. For us, it's not. If we can try, if we want to learn, tie our shoelaces with one hand, it will be artificial. Thankfully, we don't need to do that. But for her, it's a necessity. So please understand that when we talk about essential and incidental, context matters. In her context, tying a shoelace with one hand is essential. In our context, it's not. So with that, let's talk about the essential aspects of complexity in software. So one of the things that I like to do, and I'm doing right now, is I like to travel around the world and appreciate all the sights and sounds and specifically architecture. So when my wife and I went to Cordoba in southern Spain, we went to the Mezquita. And it has these beautiful arches. And the one thing you'll notice is there's repetition. The beauty here comes from the repeating elements. There are hundreds of these arches, and each arch is a double arch. There's a lower one and there's a higher one. In architecture, repeating elements are a source of beauty. And it's almost impossible to capture the beauty of the Mezquita in a picture. You have to be there to be surrounded by these arches to appreciate their beauty. There's hundreds of them, and they're all identical. They're all the same, and you're just amazed. In architecture, repeating elements are a source of beauty, as they are in nature. So the fern leaf, with many identical elements, they add to the beauty. As they are in human creations, such as this poem from one of my favorite poets, American poet, Robert Frost. This is a poem that he wrote, and the last two lines are so poignant, and trying to explain them destroys their beauty. They're the same line, but they mean slightly different things. The woods are lovely, dark and deep, but I have promises to keep, and miles to go before I sleep, and miles to go before I sleep. It's just indescribable, the beauty of those two repeated lines. Repetition in other aspects of both nature and human creation has a beauty. Compare this with software. This is repeated software. Who thinks this is beautiful? So one way to appreciate its beauty or lack thereof is to superimpose them. And the things that are not grayed out are the parts that are the same. They're not beautiful. In software, repetition is not a source of beauty. Somebody copied and pasted this course apparently to get the two different addresses much the same way. And it has none of the effect that looking at architecture has or looking at a poem has. It has all of the effect of making us laugh in this setting, or if we are dealing with this code, to make us cry if you have to work with this. In software, all elements are unique. Unlike nature, unlike other things human beings create, where repetition is beautiful, in software, repetition is a bad idea. We want every element to be unique. If there's two of something, we like to minimize it and get it down to one. That's what reuse means. Now, just to be careful, we're talking about software, pure software at its written code. there is an aspect of repetition when you talk about hardware. So you will have servers that you will replicate, or you will have nodes that you will replicate. That you do. But when we talk about written software, code, duplication is always a bad thing. We don't ever call it beautiful. You always call it ugly. This is an essential element of software complexity. It exists in software, and to my knowledge, perhaps only in software, where we think about repetition as a bad idea. Closely linked to the idea of repetition is the idea of growth. So this is a seashell, a mollusk, and it's a cross-section, so it's dead. The animal is not in here, but you can see the beauty. Of course, it's beautiful. And you can see the elements. So each time the animal grows, it grows a new world around a new segment. And as it gets bigger, it can live in this, and the outer ones are bigger than the inner ones. So as the animal grows, its shell kind of in a concentric manner grows, and it obviously doesn't have to leave its shell because it can't anyway. It would die if it had to. And of course, each one looks very similar to the previous one, except it's bigger. So in nature even, and other things that we create, when we talk about growing things up, we just make a bigger version of what we already have. Again, let's compare this with software. So here's how things start. I create a project planning spreadsheet. I'm using it, I find it useful. I talk to my colleagues and they say, this is very good, I could reuse it. Can you share it with me? Okay, so I think, okay, I'm a technologist. I'm going to put it in a version control system so that that person makes changes. They can make their changes and I can keep my changes. So now I introduce a version control system. Then somebody says, why don't you put it in a database so that we don't have a spreadsheet? Okay, so I add a database, I talk to my friends, and I say, okay, how do you connect a database? There's now a third element. Now I have to worry about database connectivity, because I have to worry about how do I get data from and to a database. Then somebody says, I need it on a web. Make a web app out of it. Okay, so I add a web engine. I do that. I have to worry about security. I have to worry about availability, fault tolerance, user friendliness. And pretty soon the original spreadsheet is gone. And what I'm left with is this very complicated system that still does project management for many projects, for many users, with security authentication. But where's my original spreadsheet? It's gone. Software, when it grows bigger, it doesn't grow big by just adding more of the same. It grows bigger in what we call, or what I call, asymmetric scaling. Asymmetric means there is no symmetry. There is no similarity in the big piece of software and the little piece. The big software that you are using for project management has absolutely nothing in common with the spreadsheet, except perhaps in the purpose. But in the internals, they are totally different things, unlike other things in nature that just grow by getting physically bigger in size. Asymmetric scaling is an essential component of software complexity. Related to this is the concept of standards. So this is a simple clock. Can you guess which way the hands rotate? Clockwise. We call it clockwise from right. Has anybody seen a clock in which the hands go the other way? No? There are actually some created just for the fun of it, because you can easily design. It's hard to think, but when you think about it, we just decided all the clocks should go this way. You can design one that goes the other way. Of course, maybe not many people would like it or be able to read it, but you can certainly design one, the numbers are all reversed. But who decided this? That all clocks should go this way? People did. At some point, we just decided, okay, the 1, 2, 3 should go this way, and the hands should move that way. Convention. We made up a rule, and we follow it. Same as with shaking hands. Everybody shakes hands with their right hands, except some Boy Scout communities that use their left hand because it's on the hard side. But most people use their right hand. Do you know, by the way, does anybody know why it's the right hand?
Because that means no harm?
Exactly. So in the old days, the right hand, especially for men, was the weapon arm. Because many people obviously were armed that day. You carried your scabbard or your sword. And extending your empty right hand was literally a symbol that I come in peace. I carry no arms. I don't have a sword or anything in my hand. I extend my right hand to you in peace. And of course, there were left-handed people around back then too, I'm sure. But everybody followed the convention. You raise your right hand and the other person does, and you shake. So even these days, are there any left-handed people in the room? Not you are. So which hand do you shake your hands with? Right hand, right? So this is a convention everybody in the world follows. Everybody, when you meet, even across cultures, like we are here in Korea, and we bow a little, but we extend our right hand. It's understood pretty much across the world. In software, by contrast, there are no conventions. So here's a Java, so computing the length of something. So if I see how many letters in this kind of letters of these cushions, so there's 4, so I can count 1, 2, 3, 4. How many chairs I can count. So counting things is a very simple problem, right? Even little babies, kids can do it. You would think it's a simple problem. Notice how many ways there are. So in Java, counting things in a collection comes in this many flavors. For an array, you call the length member function. For a list, you call the size method. For a string, you call the length method. Notice it comes with curly braces, not to be confused with the length member function. And arrays, you can do another thing. You can call the getLength method on the array with an object array, and that'll do the same thing. What problem are we trying to solve? We're trying to count things. And notice how many ways Java gives us to do the exact same task based on nothing. Really, there's no real reason you can say, why is it so different to count things? That's because in software, things are arbitrary. We just make up things and we go along. And different people make up different rules, and pretty soon you have the kind of confusion that you get. Arbitrariness, the lack of a consensus, is an essential part of software complexity. Because of the nature software represents thoughts in our mind. And this aspect, the software represents ultimately an idea that I have in my head. I have an idea for representing some problem and I code it. Leads to other differences. Like what? Let's talk about chemistry. What is this? Water molecule. See, everybody guessed it. You guessed it correctly. This is a water molecule representation. It's not a real water molecule, obviously. It's a representation. So it gives you a lot of information. H2O, it tells you which elements, as in the elements, chemical elements are part of it, in what proportion, so 2 hydrogen atoms and 1 oxygen atom. This diagram gives you the information about the angle in the bonds between the two, and also gives you the mean distance in picometers between each bond. It's a very good representation of a water molecule. It's not a water molecule, it's a representation. I showed it to you, everybody knew what it was. There's a standard representation for water, everybody recognizes it. Even for complicated things, we have representations. So this is a blueprint for an automobile. This is a standard way we represent automobile blueprints. Engineers talk about it this way. Even in the manuals you get with new cars, you can find pictures like this with different information about the wheel size, wheelbase, and those kind of things, if you're interested. Now again, come to software and talk about representation. For very simple things, you may have representations. Does anybody know what this is? What this represents? This linked list, a doubly linked list. What is this? What do you call this?
Flow chart.
Just a flow chart. And what is this?
Loop.
It's a loop. It's a for loop. So for very simple things, we have standard representations. I didn't explain any of them. I just showed you the picture. And just like the molecule, I asked you what it is, and you identified. So this is a doubly linked list. This is a flow chart. That's a loop. But as software gets complicated, anything more basic than, or less basic than this, more complicated than this, the picture becomes fuzzy. How do we represent software? We know how to represent a water molecule and a car, and maybe even simple software constructs like linked lists and flowcharts. But what about a whole project? How do we represent a big project? Is it a set of story cards laid on a table? Is it a really, really big flowchart? Is it a set of object and class diagrams? Is it a bunch of graphs that represent our progress? Or is it all of the above? Or is it none of these? Or is it something totally different? How do I represent software? Even by showing code, I can't show this kind of data, or I can't show how I'm doing against the user's requirements, or certainly I can't show this abstraction. So it sounds like I can have different representations. They all seem useful, but is this a complete list? Is this even a correct list? In software, representation is an essential problem. It is difficult to represent software. If you think about it, even the source code that you think represents software does not really. In most cases, that gets compiled or interpreted into a lower level language. So even that is an abstraction. So what is software? In a very real sense, we don't know what it is. It's a combination of all these things we think, feel, and touch, which maybe represent some underlying reality that software is. We're acting on software through all these veils, through all these barriers that we have, and hopefully we are talking about the same thing. Because often we're talking about merely representations. Another thing that's inherent about software is all the things it takes to create it. You have requirements, you have people, staff, you have tools, you have development practices, coding criteria, you have management practices, working hours. Some people have to work late and kind of answer bosses' requests. You have programming languages and human languages. Human languages are important, something we're actually working with and trying to overcome while we are training here, obviously between Korean and English. And all those things change. It's not just the fact that they are all those things. They change all the time. Languages change. Even human languages change. Of course, computer languages change all the time. People change. Teams change. Everything in software changes all the time. Change is not something that may happen. As they say, if you can count on one thing that will happen, it's that nothing will be the same in software. Something will change. It's guaranteed. The requirements will change. The language will change. Your team members will change. Your surroundings will change. Change is the only constant. We cannot fix things in software. So these are the 5 essential complexities that are very inherent in software we've talked about. The fact that it has unique elements. The fact that when you scale it up, it is asymmetric. The fact that all the rules are made up, they're arbitrary. And the fact that representation is hard, if not impossible. And the fact that on top of all of this, everything keeps changing all the time. These things are inherent to software. You cannot eliminate them. We cannot eliminate them. This is what software is in its very essence. Now, there are some kinds of complexities that are made by human beings, by us. They are the incidental complexities. What are those? Let's start with something you guys might know. What is this? Do we know the game for this? Work breakdown schedule. The technical term for it is the Gantt chart. So when I look at this Gantt chart and how things are aligned, I'm reminded of another very similar picture from the physical world. A row of dominoes. All it takes is literally I sneeze on the first one and they all fall. And this is, by the way, this is how reliable your Gantt chart schedule is. Somebody sneezing that is falling sick is all it takes to destroy your whole work breakdown schedule. The work breakdown schedule is a row of dominoes laid upright next to each other. All it takes is one accident, one thing that you didn't expect. Somebody falling sick. You can count on people falling sick. If there's any constant, somebody in your team will fall sick and will miss work. And then this will what happens. So planning, or the way we plan, is a problem we have created for ourselves. This is not inherent in software. It's a decision we make in certain teams to plan like that with the WBS and the Gantt chart. So we add this complexity upon ourselves by planning in a way that we know is not going to succeed given all these changes that we talked about. We know about the way everything changes, yet we plan in a way that assumes that nothing will change. Kind of seems at odds with reality. Another thing that I'm inspired by in software that actually is done in things outside of software is the ability to change. So this is, again, on the same visit to Spain, my wife and I went to this beautiful museum in Madrid, which has a lot of works by Picasso. So he has a very huge mural, a painting on the wall, which is called Guernica, which is about his experiences in the Spanish Civil War and the atrocities that were done in that war in the 30s and 1930s. So he painted that in the late 1930s, but he didn't just take a big sketch of canvas and start painting. He sketched it. They have these sketches in the same museum, which I found even more interesting than the actual big mural. And it's a huge mural. It's about 30 feet wide by about 10, 12 feet high. It takes up a whole room. But these sketches are small and tiny. They're like on A4 size paper, and they're around the room. So this one he did on May 1st. You can barely make out anything. And this is the one he did the next year. Now you can see certain forms emerging. So there's a bull, a hand with a lamp or something in it, another creature on the bottom. So he started refining his thoughts. Every day he would sketch and improve. Even when he started painting the entire thing, he did this in layers. It's very fascinating. So this is a picture from his studio. This is an old picture that he called them states. So this is the fourth state after he applied the fourth layer of paint to it. It's a huge mural. And you can see a lot of forms are emerging. It's a very dark image, literally black and white with kind of bombs dropping and then different figures. I want you to notice this human leg in the corner. It's angled horizontally, right? So this was the fourth state. This is not the picture you can see today. If you go to Madrid today and go to the museum, this is what you see. Notice the leg? He changed it. For some reason, he was the artist. He decided it didn't fit his mental vision. He changed it. He designed the painting in what we would now call an iterative and incremental way. He actually applied a layer of paint that had the leg horizontal. Maybe didn't like it, didn't appeal to his artistic sense. He changed it. This act of continuous refinement, I find ironically, is done more often by people in other areas like art and in literature, where people, when they write novels, will write a rough draft and then refine it, and maybe you have a second edition and you make changes, than by us software engineers who probably have more reason to do it. We, for some reason, don't refine our software. We think of it as a bad idea if we say, well, let's get something out first that is working, and we will refine it as we go along. This lack of refinement, this insistence on we have to make it perfect, we cannot make a mistake, is something we have created for ourselves. This is a mental blocker we have. This is not inherent in software. This is part of the incidental complexity we have taken upon ourselves. Related to this is the idea of design, where we organize our teams usually in this way, which is we have a management in the middle, and we have design, test, code, and analyze, and these are being managed by the management team. This is how we usually organize ourselves, a central management person or group that tells everybody what to do. Now, obviously, we can change it, and what we recommend is you make it a little bit more collaborative thing where there is maybe management in the middle, but collaboration is happening across these roles. This comes from a recommendation that's called Conway's Law, which is a rather long name for basically saying that teams produce software that looks like the teams. So if you have a lot of the teams isolated from each other, they create software using modules and representations that are also isolated from each other. So we like collaboration, and eventually you may get to a point where management is just one part of the piece. It's not a special piece in the middle. It is part of a collaborative way of doing things. So the way we organize ourselves is, again, a decision we make collectively. It is not inherent in software. It actually is a way we choose to do it. So these are all the complexities we talked about, the 5 essential ones and the 3 incidental ones, planning, refinement, and organization. So what do we do in face of all these complexities? We work like this. Create a mess. So this is chaotic. This is an agile team room. This is actually literally a team room from ThoughtWorks in, I believe, the Chicago office. And this is certainly not as clean a space as this. But this is how we work. And the reason there is this chaos, in the middle of this chaos is this notion of fluidity. The notion of being able to move around, being able to do things on an as-needed basis, both as a person and as a team. We want people to be able to move around to deal with the complexity that we talked about. So one thing that when we talk about fluidity and the ability to move around, people think, well, who's controlling all of this? Where's the control? And the chaos seems like, the appearance of chaos seems like real chaos from the outside. People think, oh my gosh, it's like a prison. There's no order. Everybody's doing their own thing. So what is our defense against actual chaos versus if it just looks from the outside as chaotic? That's okay. If within the team, if it's working, that's fine. But how do we ensure that the appearance of chaos doesn't become actual chaos? We do it through skills. So here are sand painters. And you might wonder, how do they not sneeze and destroy their work? And how do they not destroy each other's work? They're all collaborating on this extremely delicate work of art. It's all sand, it's colored sand that they may use it. Clearly, it's a job of skill. Our defense against chaos is skill. By empowering our people and ensuring they have the right skills, we guarantee that what may look like chaos is actually a very productive, fluid team. Another thing that we value in agile teams is their ability to show and reveal everything about themselves. So we have build monitors that reveal red and green builds. We do customer showcases. We discuss our problems and shortcomings and ways to improve openly in retrospectives. And we have daily stand-ups. All these meetings about sharing, all these tools to share things, the openness leads to transparency. In agile teams, we don't hide stuff. We don't hide behind anything. Even things that are not very complimentary, even things that are not very nice, that may reveal problems. Because revealing problems, admitting problems, is the first step to solving them. If we don't admit something is wrong, we will never find a solution. So the aspects of agility that allow us to deal with the aspects of complexity are these three. We have fluidity between amongst teams as well as in individuals. We value skill a lot, and we are transparent. Those are our best bets against the incidental and essential complexity. This slide and these three things to me are the meaning of why, given all the aspects of complexity that I talked about, a skilled, transparent, fluid teams of professionals is our best offense against complexity, both incidental and accidental. Complexity is inherent to software, as we have seen. There are aspects that cannot be removed, and there are aspects that through human design, we have done that. There's a type of simplicity that is on this side of complexity. That is the overly simple aspect of simplicity, where we try to just add more control, more management, more metrics. That's false simplicity. That's not real simplicity. That's just a shadow. As they say, there's a saying that I would not give a fig, a very small amount, for the simplicity on this side of complexity, but I would give my arm for the simplicity on the other side of complexity. We cannot just eliminate complexity or wish it away or treat it in a superficial manner. The simplicity that we want to have, unfortunately or fortunately, lives on the other side of complexity. We have to go through these aspects of complexity of software, and only then can we value simplicity. So I promised that I will talk about Oliver Wendell Holmes one more time, and that quote is actually his, that I would not give a fig for the simplicity on this side of complexity, but I would give my arm for the simplicity on the other side of complexity. And that, to me, in a nutshell, summarizes what agile teams are about. They're about simplicity, but they don't ignore the complexity that they have to overcome before they get there. Thanks for listening. If you have any questions, I'm happy to answer.
질문